Okay, this is page 22, number 7. Alright, how many, I'll just flash that up here. How many odd 4-digit numbers, all the digits different, can be formed from the digits 0 to 7 if there must be a 4 in the number or if there must be a 5 in the number? Okay, so we're working with these digits right there, and must have a 4 in number, and they're also saying 4-digit, all different, right? And they're also saying they have to be odd. So that means it has to end up with an odd number. So you have 1, 2, 3, 4. So we know there's a 4 in the number, and we know it has to end with an odd. So there are 1, 2, 3, 4 odd numbers to play with that we can put in there. So there's 4 choices on the last digit, and then we have to have a 4 in the number. That 4 could go in the first position, or, and they're not repeating, they're all different, it could go in the second position, or it could go in the third position. But here we're dealing with odd, so it cannot go in the last position. If 4 goes in the last position, we'll have an even number. So those are all the cases for a 4-digit odd number with 4 in the middle. So here we're down to, we have 8 numbers in total to work with. 8 numbers in total. Oops. So we're down 2 numbers, so 8 minus 2 is 6, and then we're down another number, that's 5. So 4 times 30 equals 120. Thank you. Okay, now here there's no 0, so that means we're down 3 numbers, so 8 minus 3 is 5. Now we're here, we can now use the 0, so we don't drop down to 4, we stay at 5. No 0, but 4 comes back into play here. So similarly here, no 0, so we're down the 0 and 2 other numbers, so 8 minus 3 is 5. And then we have 5 numbers left. So this equals 100. 25 times 4 is 100, and 25 times 4 is 100, so it's 320 ways. Now, if we must have a 5 in the number, that's a little different because it's odd, and we can have odd in the 4th place. So we can have 5 in the 4th place. So we're going to go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. We could have a 5 there, a 5 there, a 5 there, a 5 there. So sometimes it's just easier to use a picture. Here it has to be a 4-digit odd number. Always remember, do restrictions first. If they want odd, you deal with the odd, okay? So here there are 4 odd numbers, but we used a 5. So here we only have a choice of 1, 3, 7. So there's 3 choices there. Here again we used a 5, so there's 3 choices. Here we used a 5, there's 3 choices. But here there's only 1 choice, right? Because we're very specifically dealing with the 5. Okay, so here there's 8 numbers to work with. We're down 2. That leaves 6 times 5, and that equals 30 times 3 equals 90. Here, no 0. So we're down 3 numbers. So 8 minus 3 is 5. And here the 0 pops into play again, so that's 5, and that equals 150. No, that equals 75, I'm sorry. 3 times 25 is 75. So this one is similar to the one above. No 0, so you're down 3, so 5. 0 comes into play, it's 5, so that equals 75. Here you're down one number and no 0, so you're down two numbers. That's 6. Now we can pop in a 0, and that's 5. So that's 180. So if you add those up, you should get 420, is it? Okay, can I explain anything better? This is 5 in number. Do you see how the way I lay it out here is your communication on a test? That you communicate like this. There's no standard way to communicate on these sort of problems that come in from all over the place. So this is the way to communicate. If you lay it out like this, I know what you're doing, I see what you're doing, and you're communicating to me what you're doing. Can I take up any other question? Anything from... Yes? 11 on page 21. Okay. So the thing to realize about this one, he's going to have a knot right in there, right? So the thing is, that knot acts like your fixer. So this is a leather wristband. It's something you can flip. So this is n minus 1 factorial over 2. Oh, I'm sorry. Okay, this is page 20, number 11. Oh, my bad. I'm sorry. Okay, page 21, number 11. Okay, so it says solve for this expression here, for n is in the element of natural numbers. You know, different websites, different textbooks will tell you natural numbers starts with a 0, but others will say it starts with a 1, so it's hard to know. Either way, we'll be okay when we do the problem. I always thought natural numbers were counting numbers, so that they start with a 1, but whatever. It is what it is. There's some controversy there, some ambiguity. So we're proving this statement 2n plus 4 comma 3 equals 2/3 p n plus 4 comma 4. So you know we're using the NPR formula, which is n factorial over n minus r factorial. Now when you're proving, what you want to do is separate the left side from the right side. So let's start with the left side. We'll simplify as much as we can on the left side. So we go 2n plus 4 factorial all over 2n plus 4 minus 3 factorial. And that will equal 2n plus 4 factorial all over 2n plus 1 factorial. Oh, this is solve the expression. Why didn't you tell me it was solving the expression? You
could do it like this. You just have to, once you do the right side, just do therefore they equal each other.
Oh, okay. Okay, we'll do that. So let's, oh, good grief. Okay. 2n plus 4. You have to help this old lady, you know. 2n plus 3. 2n plus 2. 2n plus 1 factorial. So you bring it down to the denominator, and you can divide it out. So we are left with 2n plus 4 times 2n plus 3 times 2n plus 2. Now, the trick to this question is realizing, now that we got rid of the factorial, you can factor out a 2 and you can factor out a 2. So let's do that. That's going to be 2 times n plus 2. That one we can't factor anything, but this is 2 times n plus 1. So that's going to equal 4 times n plus 2, n plus 1, 2n plus 3. This will help us solve. Okay, that's the trick to this question, is just factor out what we have. Just factor all the way as far as you can go. Let's do to the right side. Okay, so we have 2/3. Don't forget that 2/3. We're going to go n plus 4 factorial all over n plus 4 minus 4 factorial, which is equivalent to n factorial. So that's 2 over 3 times, I'm going to bring this down to the denominator, n plus 4, n plus 3, n plus 2, n plus 1, n factorial over n factorial, and that divides out. So let's equate those two guys, shall we? Why not? Okay, we have 4 times n plus 2, n plus 1, 2n plus 3 equals 2/3 times n plus 4, n plus 3, n plus 2, n plus 1. So now, because we did a bit of factoring, right? Here we factored out the greatest common factor of 2 in those two. Now we can see we can start canceling. So n plus 1, n plus 1, n plus 2, n plus 2. Okay, so we have 4, that's 8n plus 12 equals 2/3 times n squared plus 7n plus 12. So why don't we multiply both sides by 3? That means we'll have 24n plus 36 equals 2n squared plus 14n. We should divide both sides by 2, but that's okay. We can do that later. 2n squared plus 14n plus 24. Notice we can divide everything by 2. Let's do that to avoid headache. That's 12n plus 18 equals n squared plus 7n plus 12. So 0 equals n squared minus 5n minus 6. 0 equals n minus 6. Now we're going to factor n plus 1. So n equals 6 or n equals negative 1. We cannot have a negative n, right? This is about counting. You can't have a negative number of objects. So therefore n equals 6. Um, yeah, okay. It'll be exact. Yeah. I don't, I won't make your test ambiguous in any way. Okay, was there anything else we could go over? Number 11 on page 20? Oh, okay. Yeah, okay. Make sure I get the right 11 this time. Okay, number 11 on page 20. Okay, the trick to this question is realizing you have an extra knot on there, right? And because it's number 11, it's a wristband. That's something that can be turned around. So you use that formula for keychain formula or necklace formula or wristband, whatever. Now there's 12 beads of various sizes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now you actually have 13 things on this necklace. So that's 13 minus 1 factorial divided by 2, and that works out to be 12 shift factorial divided by 2. I get 2, 3, 9, 508. Okay, so it's 239,500,800. That's your fixer, and these are all arranged relative to the knots. Absolutely. So, not to undo this student's wonderful work, would you like to see the calendar question on YouTube? Okay. I wish we videotaped you. I will not mention your name for uh, privacy concerns. Okay. In the calendar question, this is page 20, number 15. The problem with calendar where CA has to be together, you have this floating A, which is a part of what has to be together. And that confuses things. So just momentarily, instead of looking at calendar, let's look at a three-letter word, ACA. Just like that. Let's just look at that three-letter word, and AC must be together. Okay, so if AC has to be together, you know, it could be like this. That floating A could be there or there, but AC could be together like this, and that floating A could be there or there. Now, when we have arrangement questions, we want different possibilities, right? So the problem with this possibilities, these two are not different. And the issue arises because of this floating A, so we have to account for this ACA situation. We have to subtract it because normally when you do this question, as you know, you group AC together, you're arranging two things, two factorial ways to arrange two things, but AC could be ACCA, two factorial ways to arrange AC, which is together, and that equals 4. But you can see in this case, this does not give the correct solution, right? We have double counting here, and we don't want double counting. So what we have to do is subtract all cases involving ACA. So we have 2 factorial minus the ACA situation, which is only one way, right? In this case, we kept it nice and, right? It's only, we want one of the ACAs, we just don't want this second one. So that equals 3. The correct answer is 3. Okay, so that's why we have to account for the ACA in the calendar question. So here we go. It says here, calculate the number of permutations of the word calendar in which C and A are together, N and D are not. C-A-L-E-N-D-A-R. C and A together. So we'll go cases where C and A together, and we will subtract CA together, ND not together. Okay? So, if C and A are together, we have 1, 2, 3, 4, 5, 6, 7 things. 2 factorial ways to arrange this. But the problem is we have the ACA problem, right? We have the ACA problem. So we will subtract ACA. Okay, so we'll subtract ACA. So we have 1, 2, 3, 4, 5, 6 factorial ways that we can have that second ACA. Now we're going to subtract CA together and ND together. Yeah, that should be together. Yeah. So we end up with it being not together. So calendar. So we're going to subtract CA together, ND together. Okay, so we're arranging 1, 2, 3, 4, 5, 6 things. 2 factorial ways to arrange CA. 2 factorial ways to arrange ND. But we have to subtract the ACA situation. L, E, N, D, R. This we don't worry about rearranging that because we only have two ACA scenarios here, so we just want to subtract one. So this is DN. There's 2 possibilities here. So you subtract 1, 2, 3, 4, 5 factorial, 2 factorial for the ND, and when you do that you should get your answer, which is 6720. So that was page 20, number 15. Were there any other questions you'd like me to record? On page 20, number 9. Sure, why not? Page 20, number 9. How many natural numbers less than 10,000 include at least one 9? I'll spell it out. Okay, so because they're less than 10,000, we're dealing with a 4-digit number, or a 3-digit number, or a 2-digit number, or a 1-digit number. So can you see that we can have leading zeros? Because if it's 0, 0, if it's 0, 0, 0, 1, the number is just 1. So we are not concerned with leading zeros. And that's because it's not saying how many 4-digit numbers are there. They're just saying how many numbers less than 10,000 are there. So the easiest way to do this is to go total possibilities, subtract all possibilities where there's no 9, and you'll have at least one 9. Right? We'll go total possibilities, subtract no 9, and then we'll have at least one 9. So in this case, 1, 2, 3, 4, the total, you have 10 digits you can work with, and numbers like 7, 7, 7, 7 are okay. Repetition is allowed, right? Because they're just saying natural numbers less than that. So it's 10, 10, 10. Now, if we cannot choose a 9, that means we can't choose any 9 here, so we're down 1. So in effect, it's 10 to the 4 minus 9 to the 4, and that should get you your answer. Can I explain anything better than that?
So this is in this case you regard 0 as a natural number.
No, because in effect is subtracted here. Because this possibility could include 0, 0, 0,
Yes.
and so could this one, because we didn't eliminate any zeros in this one.
But the fact that in the total number of possibilities you didn't use 10, 10, 10, 9. I mean, like 10 to the 4 minus 1 is counting 0, 0, 0, 0 as one of the possibilities, right?
No, we,
Yeah. So and then
Yes, I know they cancel out each other, but it's just like when you're listing the options, you're considering 0 as one of the natural numbers. How many natural numbers less than 1,000? Yeah, 10,000.
yes.
Yeah, I know they cancel out, but it's just in the so it's total number of possibilities, right? If there are 10 to the 4th numbers that are less than 1,000, you're counting as natural numbers, and that includes 0 itself.
Yeah.
So we are regarding
Yeah,
because
yeah.
like technically
There's,
speaking, if
so,
you are not regarding 0 as natural number, it should be 10 to the 4 minus 1 minus bracket 9 to the 4 minus 1.
oh, fair enough.
Yeah, I was saying that, not
But we'll
something
get
else.
the same
Exactly,
answer.
exactly. Just
That's an interesting observation.
yes,
Thank you.
yes.
Yeah. Yeah, that's an interesting observation. Thank you. Thank you for that.
This
Yeah, I hear you. Okay, are there any other questions? Anything else I can go over?